Good evening, everyone. Welcome back. It is our May Speakers Night for 2025, and welcome to Rask Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of Rask Toronto Centre, and this is our Speakers Night presentation. Just as a reminder, this is May Speakers Night, and we will be taking a short break over the summer, but the Speakers Nights will be back in September. So just for the next few months after this, you might have to watch some reruns to get your Speakers Night action. Now, this Speakers Night meeting is an online only presentation and not at our New York University meetup location. Our president, Scott Masterton, will be talking about various programs later on. But first, we have, of course, our main event for tonight. So I'd like to just go ahead and start off with our land acknowledgement and acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, a little bit of introduction for our speaker. I would like to say this speaker needs no introduction, but I'm actually going to introduce him anyways. Tonight we have Dr. Ethan Siegel, a theoretical astrophysicist by training. Dr. Siegel has many, many amazing things that he's done. I can only tell you about a few of them, so make sure to go up and check his website if you want to know more. He has had a promising research career in cosmology. He's worked in physics and astronomy as a professor, and he has now switched to doing science communication full time. He does wonderfully scientifically accurate talks and stories about the universe to convey his message to the widest audience possible. He actually founded the Starts with a Bang podcast back in 2008, which you can still find episodes for. That was back when he was a postdoctoral researcher in theoretical astrophysics. And he went on to his PhD in physics from the University of Florida. He taught at secondary and college level, and he was a physics professor at the University of Portland and later at Lewis and Clark College until about 2015, I believe. He has lots of passions for natural science, teaching, outreach, and he's looked at all kinds of ways to communicate science. He has many, many thousands of articles, books, magazines, and actually, I will just say his Infinite Cosmos book is out now, so we might hear a little bit more about that during the talk. I'm not sure, but it is topical and it's an excellent book. So, all about the universe, what we know about it, and all kinds of other great things. But I'm going to let him tell you all about the topics, including the topic for tonight's talk, which I believe will be a little bit JWST based. So, Ethan, it's wonderful to have you with us tonight. Please go ahead and take it away.
All right. Thank you so much, Elena, for that great introduction. And it's my pleasure to be speaking to you today. As you notice, I'm going to be giving you a talk called the James Webb Space Telescope, a cosmic story for the ages. And yes, I do have a book, Infinite Cosmos. I'm very pleased. This is my very first National Geographic book. It's my fifth overall, but my first one published with National Geographic. And if you take a look inside, you'll see that we have a whole bunch of sites and science, as well as the story of how the telescope was built and constructed, and many of the remarkable things that it's found and shown us about the universe. And I want to give you a little bit of sort of a behind the scenes and in depth look into what the James Webb Space Telescope is, why it's so important, and what it's taught us. And also, hopefully, by the end of this talk, you'll have an appreciation for why space telescopes and continuing to build and fly new space telescopes is so important. So, earlier this year, I got the chance of a lifetime to travel to the Canary Islands and to see the world's largest telescope, the world's largest optical telescope at present, the Gran Telescopio Canarias. And I got to go there while it was observing, while it was taking data. And you would think that's really cool. And it turns out that it was cool, but not for the reasons you think, because you walk into the telescope dome and you're not allowed to turn any lights on because you don't want to ruin the observations. And it's also pitch black and dark, so you can't see in front of your face. So I had the great idea of I'm going to take my phone and I'm going to set it to take a long exposure, and I'm just going to put it face down on the floor. And we're going to see 30 seconds later, what did we get? And here is the answer. This is what I saw. This is what showed up on my phone. And I was like, wow. So, first off, this is the coolest picture I've ever taken on a phone of all time. And I'll probably never take a cooler one. But second off, take a look at what you see looking out of that telescope dome. This deep, deep image of the night sky shows stars. You can make out some nebulae if you squint hard enough. No planets are up here, but there are planets in the sky. But this only represents a tiny, tiny, tiny fraction of all of the information that's out there to collect about the universe, because all of this is exclusively here in what we know as the optical part of the spectrum. This is the visible light part of the spectrum. That's what our eyes are sensitive to. That's what our cameras are sensitive to. Here on Earth, there are a few types of light that we are sensitive to with our best instruments. There are a few windows of the infrared and a tiny bit of the ultraviolet that you can get from the ground. And there's a big section of the radio part of the spectrum that you can get from the ground. But for the rest of it, for gamma rays, for X rays, for microwaves, for most of the ultraviolet and most of the infrared, you can't see this from the ground because the Earth's atmosphere absorbs it. If you want to collect information about the universe, there's a reason you can't just rely on the portion of light that's in the optical part of the spectrum. There are all sorts of phenomena out there that produce signals at many different wavelengths. And if we restrict ourselves to what we can see with our own eyes, we're fundamentally going to limit how much we can learn about what's actually out there in the universe. So, to combat this, we do a mix of ground based and space based facilities and observatories. Yes, on the radio, we do a great job of getting so many things from the ground. And in the optical, we do both on the ground and in space. And at the highest energies, you can do a little bit of very high energy astronomy through a trick that leverages what we call Cherenkov light. Because if you get a particle that moves close to the speed of light that comes through Earth's atmosphere, guess what? The speed of light through Earth's atmosphere is just a little bit less than the speed of light in a vacuum. And so if you travel faster than the speed of light through a medium, you're going to emit a cone of radiation known as Cherenkov light. It's this blue glowing light. And if you build a Cherenkov telescope, which they put a bunch of these outdoors, you can collect and focus that light and determine where did it come from, what made this signal out there in the universe. But for everything else, most gamma ray work, X-ray work, most ultraviolet work, almost all infrared work, and all microwave work, you really, really, really want to go to space to do it. Not having to contend with the absorption properties of the atmosphere is tremendously helpful and something that gives us more data than we can get otherwise. So I want to show you an example of why the James Webb Space Telescope, which is an infrared space telescope, is so powerful. I'm going to show you an image of what looks like a dark cloud. And you can see this is filtering through a different set of wavelengths from 440 nanometers, which is visible light, to 550 nanometers, which is visible light, to 900 nanometers, which is infrared, all the way up to more than 1 and even more than 2 microns. And you see, as we go to longer and longer and longer wavelengths, what looks initially like a big void or a big hole in the universe, it turns out to just be a cloud of dust. And when your wavelength of light gets larger than the physical size of your dust particles, the light passes right through. And so, this is a wonderful opportunity to use an infrared space telescope to see so many of the things that are blocked in optical light that would otherwise be invisible to our eyes. So, what was the idea behind JWST, behind the James Webb Space Telescope? Well, we had already flown infrared telescopes in space before. We had the Spitzer Space Telescope, which was our original great observatory in the infrared. We had the WISE Space Telescope, which is a wide field explorer. We had the Herschel Space Telescope, which looked at far infrared light. And of course, most famously, we had the Hubble Space Telescope, which, although it's most known for being an optical telescope, does go a little bit into near infrared. What the big advantage of the JWST is, of the James Webb Space Telescope, is we said, look, we're going to build a large aperture telescope because larger means both more light gathering power and also better resolution, because resolution is determined by the number of wavelengths of light that fit across your telescope's primary mirror. So bigger means better resolution, more light gathering power, and a better ability to resolve and see objects in less observing time so you can do more science. In fact, when they said, hey, we're going to design JWST, they said, well, let's look at all of the ground based and space based telescopes we've ever had in the optical and in the infrared and beyond, and let's compare the design performance of the James Webb Space Telescope to it. And they were able, oh, sorry, I meant to go forward, not backwards. And we came up with this graph. This is from the JWST source documentation. And they said, wow, look at how significantly JWST overperforms compared to Hubble and compared to Gemini and compared to Spitzer and WISE. This is such better performance. It means we can see fainter objects, objects with a lower limiting flux density. It means we can see objects across a wide variety of wavelengths. The lower line here is near infrared, the upper line is mid infrared. JWST is by far the most advanced, most sensitive observatory we've ever had in both near infrared and mid infrared wavelengths of light. So, it was very exciting as a prospect. Of course, it took a long time to design and build. We had to develop wholly new technologies. We had never built a telescope with a folding segmented mirror that could go into space. And the reason you do that is because otherwise you're limited by the size of your rocket for how big your mirror can be. But with a folding segmented design, like you see at Wright, you can fit a larger telescope in a smaller rocket. And so this is how they designed and built JWST. You also see there's an enormous 5-layer sun shield. The reason that the Hubble Space Telescope can't observe longer wavelengths of light is because Hubble is in low Earth orbit. And even though it has a reflective coating on it, right, it looks like a tin can covered in aluminum foil. And the reality is not too different from that. JWST is designed to be over 1.5 million kilometers away from Earth. It's designed to be at the L2 Lagrange point and to always have this 5-layer sun shield separating the sun facing side from the optics of the telescope. So if you're wondering, is JWST ever going to take a picture of the Earth or Venus or Mercury Mercury? The answer is no. It has to point away from the sun in order for this sun shield to work and cool it down. Because if you cool it down, that means you could observe those longer wavelengths of light. If your telescope gets too warm, you're not going to be able to do it. So, for the near infrared portion of the telescope, you only need this passive cooling, which can get you down to about 40 Kelvin. And over in the mid infrared side, you need additional active cooling that keeps you down at about 6 or 7 Kelvin. So, I've been a big fan of the James Webb Space Telescope for a long time. In fact, 5 years ago, it was my Halloween costume. I made my own JWST costume, and I was very pleased with how it came out. I got all 5 layers to the sun shield, and I have you can't see it, but that secondary mirror is gold as well. You have to reflect it just the same way you do it. By the way, I know a lot of people look at the JWST and see the iconic gold color. Surprise, surprise, the whole telescope only has about 48 grams of gold in it, or about a golf ball's worth of gold. And that's because it's a very thin coating of gold on the telescope mirror, only about 600 atoms thick. So, very cool stuff. JWST, even though we often call it NASA's JWST, the reality is it was assembled and had contributions from all over the world. There were dozens of nations and hundreds of member institutions that participated in this, including the Canadian Space Agency, including the European Space Agency. And you can see from the map here that this really truly is, like all of science, an international endeavor. In fact, to get the James Webb Space Telescope from where it was built in the United States, um, we had to ship it across the Pacific Ocean, through the Panama Canal, and over to the spaceport in French Guiana. This was a 16-day secret journey at sea that was not shared. The plans for the journey were not shared with anyone because of the danger of pirates. We had to protect the James Webb Space Telescope from pirates. And who was responsible for that protection? Believe it or not, it was the French Foreign Legion, because the spaceport that it was being launched from was in French Guiana, with a European Space Agency slash Ariane Space launch vehicle. Now, I don't know how many of you watched this, but it happened almost exactly 3.5 years ago. It was on Christmas morning, for those of us here in North America, of 2022. No, of 2021, that the James Webb Space Telescope launched. And I was watching this on YouTube, and I got to learn a French word watching this. Apologies to all the Quebecois out there who are like, how do you not know French? Sorry, I live in the United States. We all learn Spanish. So I was watching this and I learned the French word nominal, because the rocket had a designed trajectory that it was supposed to follow. This was a very stressful moment, by the way. The Ariane 5 space rocket had 82 consecutive launches. And then the 83rd launch, which was the one right before the James Webb Space Telescope was supposed to launch, failed. The trajectory was off by about 7 degrees, which caused the rocket to launch the payload into the wrong place. If this had happened to JWST, the mission would have been a total loss, because it didn't have enough onboard fuel once it was released by the rocket to correct its course enough to successfully bring it to the L2 Lagrange point and put it into a stable orbit where it can do its mission. So, as the word nominal rang out, and as the actual trajectory began to trace the expected trajectory perfectly, I started to get very excited. And then the great moment happened. At the end of the stage 2 part of the rocket flight, the telescope was released from the rocket. And this is the image that we got to see. And this is beautiful, right? They equipped the second stage of the rocket with a camera so it could watch JWST floating off into the distance. Now, The first thing that was supposed to happen after separation wasn't supposed to happen for at least 5 minutes. And that was the solar panels were expected to deploy. It has a battery on board, this spacecraft does, and the battery is really only meant to be used for deployment of the solar panels. But what I saw was something different. And if you were watching this, you saw it too. The solar panels started deploying almost immediately, just seconds after spacecraft separation. And you might say, oh no, what's wrong? No, nothing was wrong. This happened because the spacecraft was launched so perfectly close to its actual designed ideal trajectory that there was almost no need for an initial spacecraft burn. There was no need to orient itself. It was already perfect. So that solar panel came out immediately. And what this meant that only a few people knew, but was hugely important, is that instead of having a 5.5 to 10 year science mission lifetime, which is what it was planned for, because we assumed we would need to use a lot of this onboard fuel that you need for science operations. We expected that we'd need to use a significant amount to correct its course, to get it into orbit. When those solar panels came out immediately, that told us, you know what, this launch was so good, we can expect 22 to 23 years of science operations. So keep this in mind that as I go through this talk with you, we have almost 2 full decades more of JWST science to look forward to. So if you're thinking like, oh, they didn't find what I was hoping they would find yet, give it more time. I'm going to show you the very rarely seen very first image taken by JWST. And here we go. Are you not impressed? No, you're not impressed. Well, I'm pretty impressed by this because what looks like a random smattering of unfocused points of light was actually proof that this telescope is working. If you take all of these bright images that you see across your screen, each one of these images corresponds to one of the 18 JWST mirror segments. All of the segments are focusing on the same star. So what they said is, okay, this is great. Now what we have to do is we have to course phase the image array. And then when they did that, they said, oh, look, now all our mirrors are pointing in the same direction. You'll notice that these 18 star images look very much like the 18 segments on JWST's primary mirror. And then they said, okay, now we're going to do fine phasing, where you take the actuators on the back of each mirror and you morph the mirror to be the exact shape you need to produce a true star instead of an aberrated image. And then you say, okay, great. What I'm going to do now is synthesize or focus all of these individual images together to create one image of the star I'm observing. And there it is. That's your completed image stack. Now, they could have stopped here and said, that's great, and we're done. Perfect. No, they went further and said, we want to expose this for a long period of time, for about 2,000 seconds. So we really get good alignment, we really get good focusing, but also so we can test the optical performance of JWST. Because you can see there's not just a star here, there are also what looks like, some other sources of light in the field. And when they perform the 2,000-second integration, this is the image that came back, which is amazing because it's not just this bright star and a weird spiky pattern you see around it. You can see a whole slew of other stars that also have spikes around them, as well as galaxies, as well as an enormous number of background galaxies. And this was our first indication of just how exquisite the optical performance of JWST is. So you look at this and you say, okay, well, I notice there's 8 spikes coming out of my star. Why is that? The scientists who were working with JWST, who were on the instrument teams, who knew this is what you were going to be dealing with, came up with a lovely name for this spike pattern. They called it the nightmare snowflake. And why is it a nightmare snowflake? Well, if you just had one circle, you would just get a point source for all your point sources of light with concentric ring patterns around them. And that's because light is a wave and waves exhibit interference and diffraction. And so that's what you're seeing is that interference pattern. Well, JWST is more shaped like a hexagon. And so that's why you get six big spikes. And then you say, well, technically it's a tiled hexagon and there are gaps within it. So the shapes get more complicated. And then you have a secondary mirror that you have to hold in place. So they used three struts. All right. Hubble, when you look at Hubble, it has those four spikes because it has a circular mirror, but it has four struts that hold it in place. JWST has three that are aligned at the specific angles they are, so that two of the struts, the spike they produce, are lined up with the six spikes that already exist. And then that smaller horizontal spike is a result of that vertical strut that holds from the top down. And so this is rarely released, but I was able to obtain a full color composite image of that initial star field. And you can see this is more than just a calibration image. This image, at the time it was taken, before other JWST images were taken, was the sharpest, deepest infrared space telescope image ever acquired. So, just with the calibration and commissioning data, there was so much science that we could have done with this data if we wanted to. Now, we're actually going to do science with the science program, so there's no need to extract science from this, especially with 20 plus years of data coming. But the data is so good that we could. This was the sharpness check, and this was one of the final commissioning images that were released before science operations began. And to those of you who maybe want to remember times when Canada and the US were a little bit of better friends than might be going on in 2025, it was in July of 2022 that the very first JWST science image was released. And you could see then President Joe Biden, then Vice President Kamala Harris, along with NASA Administrator Bill Nelson and a few other people. And there in the center of the screen, you see the very first JWST science image. In fact, fun fact that I probably shouldn't tell you, but I will, is that when we wrote this book, Infinite Cosmos, we got a request from the White House that the vice president would like a copy to display in her office. So if you want to imagine an alternate universe or a different pocket of the multiverse, maybe, where America is run by President Kamala Harris, that is the same version of the United States of America that just possibly has a version of this book that has a book about the James Webb Space Telescope in the Oval Office of the White House. I've not gotten any word from the current administration that they would like one, but phone lines are open, people. So I want to show you just how much better this was. This was the Hubble image of that field of view. Hubble took data of this image of this galaxy cluster, which is named SMAX 0723. Hubble took this image, but JWST's image revealed so much more. And this is kind of the story of JWST. You reveal more in longer wavelengths of light, and this includes revealing objects that are too faint, too cool, or too redshifted. Because you remember, light is defined by its wavelength, and as the universe expands and light travels through it, that light gets stretched by the expansion of the universe. So JWST is optimized to find cooler, fainter, and more distant sources than all the observatories that came before it were sensitive to. So we see this, for example, when we look away from the center of the Milky Way. This is a star cluster known as Digel 2, and I am showing you two different views of it. A very blurry looking one from the Spitzer Space Telescope, and a brand new one from the James Webb Space Telescope that shows a whole bunch of features like individual stars and outflows from young, newly forming stars that we never could have seen with more primitive technology. This this is a protoplanetary disk known as the Hourglass Nebula. The disk is in the center, it's horizontal, it looks like that dark lane, and this is a uh, animation between near infrared and mid infrared views taken with JWST. Here's a more familiar object for all of you. It's the Ring Nebula, first as imaged by Hubble, then as imaged in near infrared light, and then as imaged in mid infrared light. You can see there's a whole slew of extra features that appear to JWST's views than you could see in the Hubble view. This is why we look in different wavelengths of light, because all of this information from the universe is out there, and you don't want to miss it by restricting what you can view. You'll remember the famous pillars of creation. This was them as imaged by Hubble on the left in optical or visible light, and on the right in near infrared light. You can see it becomes a little bit transparent in near infrared light, except where the dust is thickest. But when JWST looks in mid infrared and near infrared light, you can see an enormous difference in detail. I'll show you again. These are Hubble's views. These are JWST's views. On the left is mid infrared light, which primarily highlights the cool gas and dust, and where I love that you can actually see a glowing star, a glowing, newly forming star over in the tips of the pillars, right here, right here, right here. These are revealed in mid infrared light. But over in near infrared light, you can see both the ghostly outline of the pillars and the stars behind them. This is such a rich view. I'm so glad we have this. We also can look at galaxy clusters, right? Galaxy clusters aren't just collections of galaxies, they're also incredible sources of gravity. And one of the things gravity does is it distorts and bends and magnifies the light from objects behind it. So this is not a snake eating a galaxy. This is a galaxy whose shape is distorted and extended by gravitational lensing. This thing that looks like a light up light stick being shaked back and forth is not. It's a galaxy that actually appears multiple times due to the distortion induced by the gravity of gravitational lensing. And these long, thin, wispy strands, they're a galaxy, oftentimes the same galaxy stretched into multiple images. So when we collect images like this, we not only get to see fascinating features about these background objects, we get to learn things about the gravity and the mass distribution of the galaxy clusters that are doing the lensing. You can see incredible details when you look at a galaxy, because you get to see, oh, if this is the Hubble view in optical light, then you say, well, we can also look at near infrared light or mid infrared light and see a vast array of different details that show you where the sites of future star formation are, where newly forming stars are being born, how dust exists and doesn't exist within the spiral arms. You can see there's many dust rich regions and then dust poor regions. And you can see that there is no new star formation happening in the very center of the galactic bulge, which is something that we wouldn't necessarily have known before we looked with an instrument like JWST has. Um, One of my favorite things is this deep field image, right? The deepest view that Hubble ever took of the universe is the Hubble Ultra Deep Field, with an exposure time of 11.3 days. And the portion that's highlighted here largely corresponds with the Hubble Extreme Deep Field, which is a portion of this image that has 23 days of observing time. But on the right is the JWST view. And you would look at it and say, why is it smaller? It's not smaller, it has higher resolution. If I just zoom in on the part of this that has the four big galaxies you can see up top over here, one, two, three, four, all in a row. Take a look at what this looks like with Hubble's views and with JWST's views, right? I'm going to animate back and forth between these two. And you can see that features that don't appear in the Hubble image, like take a look at this galaxy over here. It has no spikes in the Hubble image, but in the JWST image, it has spikes. Same things for the galaxy down here. No spikes in the Hubble image, spikes in the JWST image. That reveals an active supermassive black hole at the galaxy's center. Notice how this galaxy, when we look at infrared, looks brighter and more extended. That's because it has a large halo of stars and gas that you can't see with Hubble, but that you can see with JWST. Then look over here and here. These galaxies look bright in the Hubble image, but faint in the JWST image. That's because they are not actively forming new stars. So for JWST, they look a lot fainter. And some of my favorite things is that if you look really hard, you can see there are a few regions of space where in the Hubble data, you don't have any light, but in the JWST data, light appears. Those are galaxies that are either too faint or too distant for Hubble to see. But JWST, even with less than 1/10 of the observing time, can already reveal what Hubble cannot. So there are a bunch of finds that you'll say, like, well, look, there are things JWST was designed for, to see fainter and more distant objects than any observatory before could see. And it's done that. Back when we were entering the JWST era in 2022, the farthest galaxy we knew of, the most distant galaxy, was named GNZ11. Today, GNZ11 is the 14th most distant galaxy known, because that record was broken by 13 galaxies that were observed or measured with JWST. The record holder for about 2 years was Jade's GS Z14-0. And as of Monday, welcome to Wednesday, as of Monday, the 19th of May, 2025, this galaxy named capital M, lowercase o, capital M dash Z14 is even more distant. This galaxy comes from about 300 million years after the Big Bang. This galaxy comes just 282 million years after the Big Bang, when the universe was 2% of its current age. New cosmic record holder for most distant galaxy. And JWST has done much, much more than that. It's found the most distant galaxy cluster. Here's a protocluster just 600 million years after the Big Bang. Here is the most distant gravitational lens ever observed, where the foreground lens is farther away than any other gravitational lens ever found. Here is the most distant red supergiant star ever discovered. Right? Here is the new most distant black hole, the most distant active supermassive black hole ever discovered. Guess what? This record already has been broken twice more, by UHZ1 and by GNZ11 itself, which has an active supermassive black hole. So we can find active supermassive black holes not just 700 million years after the Big Bang, but as far back as 420 million years after the Big Bang. It's also found multiply lensed supernovae. So supernovae that we actually can see multiple images of the supernova on replay because of the gravitational lensing effects of the foreground cluster. Objects like this have the potential to resolve what we call the Hubble tension, or the fact that we don't know how fast the universe is expanding because different methods yield different results. This is an independent method that might help us resolve that tension. We also see the brightest emission line galaxy at greater distances than ever before. And you say, great, great, Ethan, look. But these are things it was designed to find. It was designed to find fainter and more distant objects than anything before it. Of course, it did those things. And I'll say, you know what? Fine, you're right. You're right. It was supposed to do that, and it did that. But that's not why we build space telescopes. That's not why we explore beyond the known frontier. We do these things because of what we don't know we're going to find. We do these things because when you look at the universe in a fundamentally new, fundamentally different way, you need to give yourself the opportunity to be surprised. If you look at the universe in a new way, with new tools, with more powerful tools than ever before, you're giving yourself the opportunity to see something that you didn't even know to go out there and look for. And oftentimes, that's where the greatest lessons and the greatest advances lie. For example, we turned JWST on this old familiar site, the Orion Nebula, but we looked with a new tool. And we were thinking, we're probably going to be able to see some cool things in there. Literally cool, like protostars that are still forming, or maybe even substellar objects like Jupiter or super Jupiter objects that haven't yet even become stars. But with the resolution and light gathering power and infrared specialty of JWST, maybe we could see something new. Well, we did see something new, including something we didn't expect. Take a look at these faint little double dots that these arrows are pointing to. Sure, there are a bunch of single dots, single dots, single dots, single dots also. We believe these are Jupiter mass-ish planets that are a few times the mass of Jupiter without any parent stars of their own. But this is a surprise. A full 9% of them appear to be bound in binary systems. You can see the numbers down here, 35, 31 through 35. These are big numbers. They found dozens of these Jupiter mass binary objects. Now, some people dispute, oh, maybe these aren't Jupiters, maybe these are larger, higher mass protostars that are just extincted by the dust. And the jury's still out there, but we never knew to even think about a population of Jupiter mass binary objects, and now we're looking at them. It's kind of amazing. This is a big galaxy cluster. For those of you who know your phone numbers, this is Abell 2744, the target of some early JWST science projects like the Uncover collaboration. Well, guess what? We talked about the power of looking at different wavelengths of light. And another space telescope that we've used to look at this, in addition to JWST, is the Chandra X-ray telescope. And when we zoom in on one particular very faint low mass galaxy, we find it has an extreme amount of black hole activity. When we look at the stars in this galaxy, because we look at the light coming from it, we find that this only has a mass of about 10 million solar masses worth of stars. That's the stellar mass of this galaxy. But when we look at the light coming from the black hole in X-rays, the black hole also has a mass of around 10 million solar masses. We had this chicken and egg question. What happened in the universe? Did black holes form first and did galaxies grow and form around them? Or do you need to make stars first? And then when the first stars die, they make black hole seeds and black holes grow from that. These observations, where you have an equal mass black hole to the stars combined in the galaxy, tell us, you can't form this from stars first and then black holes. You need a massive seed for your black hole that's at least tens of thousands of solar masses. So this has revolutionized how we think black holes first form in the universe, not from stars, but by some earlier independent mechanism. This answers the chicken and egg question, and it's something we didn't even know to think about before JWST came along. Here's a fun little thing. Some of you will remember, oh, yeah, back in 2017, we had a gravitational wave event that was two merging neutron stars. And then just after the merger, we got a blast of gamma rays. And when we did follow up observations, we learned, oh, this was a kilonova event. This was where two neutron stars merge and they explode and they produce heavy elements, and then the remnant collapses to a black hole later. Well, gamma ray bursts come in two different classes. There are the short period bursts, which last 2 seconds or less, and those are what we think we observed with this kilonova event. But there are also long period ones that last hundreds or thousands of seconds. We just classify more than two. We call these long period gamma ray bursts. And people assume these were something else, like a supernova. Well, guess what? In 2023, a gamma ray burst happened in March, and it was one of the brightest ones. So they said, hey, director of JWST, can you give us time, some opportunity to go look at this object and see what it is in follow up? And so they looked 29 and 61 days after the gamma ray burst with JWST, and they found, good Lord, we see evidence for the production of elements like tungsten and selenium and tellurium. And these events are only made in kilonovae. Does this mean all gamma ray bursts are neutron star mergers? Does it mean that some of the long gamma ray bursts, in addition to some of them being made of supernova, are also made of neutron star mergers? Yeah, definitely the second one, maybe even the first one. This is, again, not something we even knew how to ask before we looked with JWST. The universe has surprised us again. One of the biggest surprises were these. This is a small selection of galaxies, hundreds are now known as little red dots. These galaxies, if you followed JWST in the early days, people were saying, oh, we found huge numbers of bright early galaxies that break the universe, and our standard model of cosmology is wrong, and we don't even know why this is. Well, that's not how science works, obviously, but that is how some sensationalist scientists communicate to the public. And instead, what we had happen was we said, look, we need to know, why are there so many of these bright objects that are consistent with early galaxies? And it turns out that it took 4 different contributions before we were able to suss out why this is occurring. The first is that JWST was kept so clean that it optically overperformed over what was expected. Everything came back more than twice as bright as was expected because of how clean the optics were and how well the telescope's optical performance is. A second thing was on the theory side. We were making theoretical calculations that used these big simulations we ran, but the simulations were only at medium resolution. It turns out that at the highest resolution, you get these overdense peaks, these very rare but very severe, oh, the universe was born with just a little bit of extra matter over here and over here and over here, and those lead to a enormous enhancement of the earliest galaxies that form. A third thing was the incorrect assumption that star formation occurs only at this high maximal rate constantly. It doesn't. Star formation is a bursty process. Sometimes you form stars at an enormous rate that's way higher than the theoretical maximum rate because it doesn't sustain itself. You get a spike, a burst of star formation. And during that burst and immediately after, things look very bright. And then just a few million or tens of millions of years later, the burst is done and the galaxy goes back to being fainter. So bursty star formation is another ingredient. And finally, for all of these little red dots that aren't compact sources of light, but are extended sources of light, we believe there's an enhancement from an active galactic nucleus, from an active supermassive black hole in these galaxies, that brightness enhances them. And this is four separate contributions we needed to figure out in order to solve the mystery of these little red dot galaxies. Now, if you're saying, hey, wait a minute, why did you stop when you got an answer that matched with your expectations? Why didn't you keep looking for other contributions? I wonder that too. This is something we do all the time in astronomy at our own peril. It's not necessarily a great idea. There may still be more to uncover about these little red dots. But the biggest surprise was something I didn't expect and no one I knew expected. We thought for a long time that if we look at other stellar systems out there, stellar and planetary systems, they're going to be similar to our own, right? We've got some planets, we've got an asteroid belt, we've got some more planets, and we've got a Kuiper belt. And then way out there, we've got an Oort cloud. And so we said, okay, look, when we look at protoplanetary disks, when we look at newly forming planetary systems, we're curious, are we also going to see an asteroid like belt and a Kuiper like belt? And so the first one JWST looked at with its MIRI instrument, with its mid-infrared instrument, was the bright disk around the young star Fomalhaut. And what they found shocked everyone. Yeah, they found an inner belt that corresponds to an asteroid like belt. And yeah, they found an outer belt that corresponds to a Kuiper belt analog. But they also found an intermediate belt, a third belt in there. Immediately we ask questions like, oh, geez, well, are we even typical? Are we even the most common? Are two or three the only numbers? Can they have more or less? So we looked at a second star, the almost face on star system Vega, one of the brightest stars. I think it's fifth brightest in the night sky. And when we looked at it with JWST, we found no evidence for belts at all. In fact, this little dim spot you see tells us that this is where the maximum mass planet can be. Whereas Fomalhaut had gaps, which we think are evidence for, oh, you've got massive planets in there. This planet, at most, could only be about 40% the mass of Neptune. That's the most massive planet that Vega could house. And now we're asking, well, why doesn't Vega appear to have planets or belts of any type? And now we're asking, well, maybe it's because it's a rapidly rotating star, and stars that rotate too quickly have to suppress planet formation. This was an idea that people threw out a long time ago because they didn't think it would be relevant. And now it's being revived because we've looked at the universe in a new way and we gave it the chance to surprise us. We've looked in so many places and seen fascinating things. We looked inside the Crab Nebula, and what looks like smoke is actually accelerated electrons by magnetic fields that emit radiation that JWST is sensitive to. We looked into the largest star forming region in the local group and found a globular cluster in the process of being born. The single most massive star we know of, at about 260 times the mass of the sun, is in there. And while there are a slew of other sites to look at out there, I think the biggest one to leave you with is the idea that as we look out at the universe, there's the possibility that someone in one of these different distant star systems or in one of these distant galaxies is looking right back at us. And I think that's a good point to end and ask if you have any questions.
Thank you very much, Ethan. This is a great talk, and indeed, it does sound like things are very much looking up for James Webb Space Telescope, if indeed there can be said to be an up out at L2. I personally hope it continues to break that most distant galaxy record. Now, just checking for questions from the YouTube chat here, and it looks like our crew is taking them. Yeah, looking for questions. So I'll sneak one in because I know you don't have very much time today, I thought I would actually sneak in a little question about one of my favorite things that James Webb does, which is it possesses the ability to do this parallel mode observing. And I was just wondering if you had any thoughts on the parallel mode and when to use it, when to not, and maybe tell people a little bit about it.
Sure. Let me back way up over here and let's go back to, let's see. All right. So I'm going to show you this calibration image of JWST again. And this is the final image that they released before science operations began. And the reason I want to show you this is because you look at this parallel mode imaging, right? You're talking about this. What this basically is saying, look, JWST, this is the image I wanted. It collects light. So if you say, this is what my near cam imager looks like, well, if you focus on one target with over here, you get this other field known as a parallel field for free. So it gives you a chance to do bonus science. If you're looking at a galaxy cluster that's in one of these fields, you can come over and say, well, what does the region of space without the galaxy cluster look like? Sometimes if you say, well, I'm looking at near cam, I wonder what I see in mid infrared light. Well, you get this parallel field of MIRI for free. Sometimes they'll double up and say, well, I want the near cam image of what's over here, but the MIRI image of what's over here. And they'll orient the JWST to give you both of them at once. So what parallel mode observing allows you to do is it allows you to say, well, here's what I'm mostly interested in, but because sometimes you can take 2 or 3 instruments worth of data at once because the light comes in and goes into one instrument or another, or you can say, well, the light that gets focused into one instrument, that's great for that instrument, and then we'll send more light that comes in from a slightly different angle to another instrument. You get bonus science for free. And for me, that's just, yeah, it's an extra bonus. Why wouldn't you want to take care of that whenever you can? It's also a huge advantage when you want to construct these wide field mosaics, because it means you don't just have to get one tile and then tile the whole thing around. You can get multiple tiles at once. If you followed Sears, the Cosmic Evolution Early Release Survey, early release science survey, you will notice that Sears started out as just a patchwork of rectangles and eventually got filled in to be a full field. And that was thanks to the power of parallel mode observing.
Absolutely. Thanks for that wonderful answer. I think we probably have time for just one more question, and then you're going to have to run, I'm sure. We do have a question from Betty who asks there is a theory that our universe might have merged with solar systems from another universe since fully formed solar systems are unusual so close to the Big Bang. Just wondering what you think of this idea.
I would say when people say things like fully formed stellar systems are rare so close to the Big Bang, my big question is, how do you know? We've only ever seen stellar and planetary systems here in our own galaxy or very close by in like globular clusters or in the galactic halo or maybe in satellite galaxies of the Milky Way. We don't have the resolving power to detect planets tens or hundreds of millions, much less billions of light years away. So, it's always fascinating to wonder about, like, well, could there have been a universe before ours and what would the consequences of that be? And could there be remnants from that interacting with our own universe? But the fact that people are jumping to conclusions and telling you things like, oh, solar systems or stellar systems or planetary systems are rare at this early epoch in cosmic history, I would say, how do we know? We don't know. We don't have the observational evidence yet. And for me, that's what you have to always rein yourself in with, is you have to be constrained by reality. Elena, I'll do it. I'll stay for one more. Give me one more question.
All right, thank you. All right, so we'll go ahead and do one more really, really quick question, and I'm going to just make it a bit of a fun one that you maybe haven't talked about too much, other than the free floating, rogue planets. Are there any James Webb Space Telescope in our solar system discoveries that you're excited for?
One of the best things that it's been able to do in our solar system is it's been able to give us the highest resolution views of the outer gas giants, of the outer ice giants, Uranus and Neptune. We've seen them more clearly with JWST than at any time since the late 1980s when Voyager 2 flew by them. So we've got the opportunity to see Uranus transition from, because it rotates on its side, we get to see it go from solstice to equinox to solstice. We get to see these seasonal changes in Uranus at better resolution than ever before. And so for me, the ability to do not just like get these pictures of it, but to do what we call time domain astronomy and to see how does it change from one moment to the next, from day to day, week to week, or year to year, or even decade to decade. With a 23-year cumulative mission lifetime, we're going to be able to see planetary changes occurring on the most distant planets in our solar system as never before. And even though a lot of people aren't very excited, I do want to remind people there is a wonderful launch window coming in the 2030s to launch a mission to both Uranus and Neptune. And JWST data can tell us, if we're planning on doing that, what it is we should be looking for and what types of instruments we should be outfitting these telescopes and these orbiters and even possibly atmospheric probes. What should we have them optimized to look for?
Absolutely. And I know you said that was the last one for tonight, so we'll stop here. Everyone else who asked your questions on YouTube, we can package them up later and send them to our speaker. So we're going to go ahead and say, from resolving Hubble tension to resolving tension with our listeners. Thanks again to Dr. Ethan Siegel for joining us this evening and answering as many questions as he could before he had to leave. So we're going to have our last transfer of the evening, and I'm going to say that it's been an absolute joy to end off our session before the summer break with this talk. And I'm going to hand over to the president of the Toronto Rask Center, Scott Masterton, to finish off the evening. Over to you, Scott.
Thank you, Elena, and and hello, everybody. Uh, Friends, I want to thank you for viewing or being with us tonight. And as I listened to the story of the James Webb, I can recall very clearly when it was launched and how I was very tense about the 300 points of failure that it successfully completed. I'm not sure that was mentioned, but it was amazing to think that that could happen so smoothly. And what, 3 years ago? Very, very interesting. And thank you again, uh, Dr. Siegel. So now for some announcements about upcoming events that will be of interest. And I want to welcome you folks and let you know that what we do each at these recreational nights are not the one that we just had was a speaker's night, which are suspended for the summer, but we will have a RAN once a month, and it will be our members speaking about areas of their interest. And please do use the questioning function in YouTube to present questions. Also, a reminder that the Carswell Observatory tours will occur every Wednesday evening through the summer, and you can get that information at the indicated websites. The DDO has Sunday stargazing, Sunday, May 25th. The information is there, and you can view the sun safely at those times. And don't forget the 90th anniversary weekend, celebrating the 90th anniversary of the DDO telescope. Hardly seems like almost 100 years. Uh, there'll be an invitational session in the beginning in the morning which is available only by invitation, but after 1 p.m. you may do a self-tour of the DDO, which would certainly be of interest if you've never been there. And there'll be a free star party that evening. The Millennium Square public star party viewing will occur May 30th or 31st, depending on the weather, and go to the website for information on when that's to occur. And the next recreational astronomy night will be June 4th, and at the York University, and Claudio Oriani will do the sky this month. Julian Samuel will tell us about the 60 millimeter telescope, and Frank Dempsey will have some updates on the telescope loan program, which is available to members free of charge. The Bayview Village Park will have viewing, telescope viewing, Monday, Tuesday, or Thursday night, June 2nd through 5th. Check the website for go, no go. The DDO Astronomy Speakers Night, Seeing Double Stars in June on, June 7th, 9:30 to 11. Go to the website and get the information for attending and costs. The DDO Astronomy Family Night will occur, Constellations Connecting the Dots. You'll have an opportunity to view constellations and obtain information about that June 14th at 9:30 at night. The DDO Sunday Sun Gazing June 29th at 12:30 to 1:30. Safely view the sun and the sunspots. That is always of interest. And the next recreational, beyond that, the next recreational astronomy night will be July 2nd, and the attendees will be announced at a later time. And save the date for the open house and awards picnic at the Carr Astronomical Observatory, July 26th. The Carr Astronomical Observatory is available to members now. It's accessible year-round, and we've just spruced it up at the beginning of this month, so it's ready for service. And also, you can get RSC memberships at the National Office website. Oh, and yes, we run on volunteer energy, and you've seen a lot of those volunteers tonight. But you can be a volunteer to assist us in our various outreach programs. And thank you for viewing, and have a good night.